Continue. Stay with me. So today is a day set aside for you to hopefully have given some thought to how well prepared you feel for exam number 2. I know the end of the semester is a bunch of craziness and so if you're a little bit behind, or if something kind of went by and you didn't feel totally comfortable with it, I wanted to have a day where I have no agenda other than make sure that you feel like you're in a good place to be ready for Friday. And if you're not in that place yet, I'll see what I can do in, a 75-minute class block to help get you on your way. And that isn't it, right? Like, you still have another couple of days to fill in any gaps, to shoot me emails asking questions, to set up a time with a tutor, maybe even, whatever it is, if you're like, oh my gosh, I really have to do well on this exam and I'm feeling a little bit lost. There's time to rectify that feeling. I have come to today's class as I often do. Hold up, I'm trying to organize here. As I often do, fully prepared to deceive you if I need to, but honestly and truly, I will tell you that I have some questions in chat already. So I have no reason to say, hey, maybe someone has a question about this, because I would do that for your own benefit if nobody was asking questions, but I have some chat questions already. And if you come up with questions along the way, the only reason why I mute everybody is because when I get the feedback, I just can't figure out what's going on. But if you want to unmute and ask a question out loud with your voice, that is delightful. If you want to type questions in chat for all to see, that is fine. If you want to do direct messages to me because it's nobody else's business what you're confused about, that's fine too. Whatever it is, I'm happy to deal with it. So I have some questions. I'm going to start with the practice exam. How do I phrase this? I'm a little, I don't want to say lazy, because I would do anything I can to help you learn this material. Writing exam questions is not the most fun thing in the world. And so I've come up with certain types of questions that I think reasonably assess your understanding. And if I can find a question that is on the homework, and then I ask that question on a quiz, and then I put that question on the practice exam, I feel like, hey, there's a question that if you've done, XYZ along the way, you should feel supremely confident to tackle this question on the exam. And I'm happy to have some of those questions on the exam where you can tackle it and feel, like, hey, I was totally ready for that one, but now this other one I'm a little confused about, so I'm going to have to think about it. So there will be some questions that you have definitely seen before if you've done the homework, the quizzes, and the practice exam, and some questions that will be different. And, I think I can say this without damaging anyone's reputation. We had a part-time physics instructor at Salem State for a while, and he was a wonderfully enthusiastic human being and creative. Enthusiastic and creative, those are good things to be in life. But like he would say, you know what, this is gonna be a pirate themed exam. Arr, mateys, here's your exam. Oh, the bird's up in the bosun's nest and drops a shell. What's the velocity? And like that could be fun for some people. I totally get how that could be a fun thing to write the exam. And maybe if you're feeling in a really good place in life, maybe it'd be fun to take the exam that way. But goodness, students were like, oh my gosh, I was just trying to figure out what a bosun's nest was and I couldn't figure out what the physics question was. And, you know, people are stressed out. So it's my hope with the exams that I'm giving you that you're not feeling totally thrown into some different environment. You're going to see the same equations that are on the equation sheet here. You're going to see the same types of questions that are on the practice exam, that are the same types of questions you've seen on the quizzes, that are same types of questions you've seen on the homework. So you should feel, you know, at least comfortable, not disoriented when you go to take the exam. Okay, enough blether, Dr. McTaylor. Answer some questions. All right, I will. So there's an auto race, number 7 from the practice exam, which we have seen before in other contexts. So this is something that you could reasonably believe that you will see on the exam. Another thing I'll just point out right now, I haven't looked at the exam recently, so I don't remember what questions I actually did ask on it. So this question may be on there. I'm not trying to be cute. I don't remember, but it very well, this is the kind of question that I would ask you on the exam. So an auto race is held on a circular track. A car completes 1 lap in a time of 45 seconds. So right there, let me just point out some information that we're getting along the way. I know I have the answer there. Don't let that mess with your ability to think. So the period of motion is 45 seconds. That's the definition of period of motion. The capital T, it's a special amount of time for 1 revolution, 1 time around the circle. So we know the period of motion completes 1 lap in a time of 45 seconds with an average tangential speed of 30.6 meters per second. Tangential speed is like the actual velocity, the V number that we're used to seeing when we talk about speed, and it has units of meters per second. And so we have a toolbox. Let me close this for just a quick second. So we are being asked to find the average angular speed. So you will have to be familiar with the terminology that we're using, and angular speed is the omega value in radians per second, and we want to find the radius of the track. And we know, sorry, we know the time for 1 revolution, and we know the linear velocity. So when we scroll back up, or however it is that you will access the data sheet, you will see some information on the data sheet that has to do, okay, so 1 revolution is 360 degrees, that's 2 pi radians. What else do I know? I know that various information about omega and acceleration and radius and tangential linear velocity equals r omega. And then maybe because I was scared that you wouldn't understand this question for the exam, I also included a remember. If I have a remember on the data sheet, I think you should try to remember it. Since V equals R omega, then omega equals V over R. So there's all some information. The other bit of information that's kind of hidden in all of this is that linear velocity, kind of part of this, and the time for one revolution, v equals 2 pi r over t. V equals 2 pi times the radius times the time for one revolution. This is the distance around a circle. This is the time to go around a circle one time. So, oh, here it is. V equals 2 pi r over t. So that equation. So the information that you need is here on the data sheet. And if you are taking the exam and you're like, dang it, there's some equation that I'm supposed to know and I don't see it, go ahead and send me the message while you're working on the exam, and I'll try to, you know, point it out to you on the data sheet, or say, oh my goodness, I forgot to include that on the data sheet. Let me tell you the information now. So we have some information now that will help us answer the question. And so the first part, and I kind of did it the long way for no good reason, but omega equals V over R, omega equals 2 pi R over T. 2 pi radians divided by 45 seconds is 2 times pi is 6.28 divided by 45 is 0.14 radians per second. So we can figure out the angular velocity in radians per second. And then we use that other equation that we were talking about, omega equals V over R. Therefore, R equals V divided by omega. So V is the linear velocity, 30.6 meters per second. Omega, we just figured out the angular velocity, 0.14 radians per second. And meters per second divided by radians per second. Weirdly, the seconds cancels out, the radians just disappear, and we have units of meters. 219 meters is the radius of this track. Let me clear all drawings so things are less of a mess, and move on to the next question. I have a list of 1, 2, 3, 4, 5 questions that people have asked so far. If you have other questions or things pop into your head like, you went through that a little bit quick, I don't understand it, go ahead and ask, and I'll take another whack at making it make more sense. Number 9 was kind of a cutesy math problem from another textbook that would have been on somebody's homework at one point in history, and at some point I decided that I would incorporate it into the practice exam at least, because it makes a little point about angular velocity and the equations of angular kinematics. And the point that I want to make is that angular distance equals angular velocity times time. I mean, we know that, right? To go around a circle, the total angular distance around a circle is 2 pi radians. That's an angular distance. Now we have 2 people that are going to start off at the same point. One's going to walk one way, one's going to walk the other way. I would say their motivation, it's 2 people that, you know, met for lunch somewhere around this circular, you know, circular lake, I guess. And one of them says, oh my goodness, I can't find my iPhone. It must have fallen out of my pocket somewhere. And so in order to cover the whole distance around the lake and look for the dropped cell phone. The people go off in opposite directions until they meet up again. Now, one person is walking faster than the other one, but we're not going to talk about their velocities in terms of linear velocity. We could, it'd make for a more complex problem. We're going to talk about each of their velocities in terms of angular velocity of radians per second. And because they're walking in opposite directions with the ultimate goal of covering the entire angular distance of 2 pi radians, we're going to add their two velocities together. So since theta equals omega times time, the time it takes them to do this is going to be the angular distance, 2 pi radians, divided by the total angular velocity, which is each of their velocities added together. So you add those two numbers together and we get the 1.31 times 10 to the negative second. So the time it takes is going to be 2 pi radians divided by 1.31 times 10 to the negative second radians per second. And when you do that, radians disappear and seconds pops up to the numerator and we get 480 seconds. So, you know, it would have been a more direct question, I suppose, if I just said one person with an angular speed of 3.89 times 10 to the negative third radians per second is going to run around the circle one time. And, you know, we'd have an angular distance of 2 pi radians, an angular velocity of 3.89 times 10 to the negative third, and we just solve for time. Like that would be the most direct kind of question. This question is a little more complex because we have the two people going off in opposite directions and we're saying, oh yeah, it's going to be their combined angular velocity that gets the whole circumference of the lake covered when they do that. So that was, it was a little tricky, but nothing you can't handle now that you know the trick. Number 10 looks really difficult and it's not as bad as it appears. The point with number 10 and then later on number 13, the point with 10 and 13 is that we have some conservation of energy. Conservation of energy is a concept where all of the kinetic energy at the beginning will turn into a combination of both kinetic and gravitational potential in this case, or in the other case, they start off not moving, so there's no kinetic energy, all they have is gravitational potential, but that turns into kinetic energy as the gravitational potential energy disappears. So there's the big overarching concept. If I take a ball and drop it, it has potential energy that turns into kinetic energy as the ball falls down. If instead, I don't have a piece of wood here to do this, but if I instead roll the ball down my arm, if it's rolling, then it's got potential energy and linear kinetic energy, but also this rotational rolling kinetic energy, which involves more math. So that's what we have here. The ball is initially rotating and what we say translating. It's rolling, but it's also moving forward. So it's got two types of kinetic energy at the beginning. And those two types of kinetic energy are 1/2 mv squared, that's the linear motion, plus 1/2 I omega squared, that's rolling kinetic energy. Now, I is the moment of inertia. It's the angular mass for a bowling ball. So 1/2 I is 2/5 mr squared, 2/5 mr squared times omega squared. Well, the other thing, and I mentioned this in a previous problem, and we will use it again and again, is that we have this relationship between rotational velocity and linear velocity. And so 1/2 times 2/5 mr squared times v over r squared, which is 1/2 times 2/5 mr squared times v squared over r squared. So for the, that's what I have written down right here, the 1/2 times 2/5 mr squared v squared over r squared. So r cancels out, r squared cancels out. Mass appears in every term, so mass cancels out. And we come up with a simplified equation. So when mass cancels out, we have 1/2 v squared, that's the initial linear velocity squared, plus 1/2 times 2/5 r squared, v squared over r squared, equals GH. At the top of the hill, it gained gravitational potential energy, and it is also still rolling. So it has linear kinetic energy and rotational kinetic energy, even at the top of the hill, the top of the bowling alley chute, as it's still rolling. When we cancel out the radius, we get 1/2 v initial squared plus 1/2 times 2/5 v initial squared equals GH plus 1/2 v final squared plus 1/2 times 2/5 v final squared. 1/2 times 2/5 is just 0.2, it's just a number. 0.5, that's 1/2, plus 0.2 is 0.7. So everything simplifies quite a bit right here. 0.7 v initial squared, 0.7, and the initial velocity was given, 6 meters per second. So 0.7 times v initial squared equals GH plus 0.7 times v final squared. G and H are just numbers. G is 9.8 meters per second squared. H is the height of the ramp. So we plug in those numbers. We have numbers for everything except for whatever the final velocity was. 25.2 equals 5.39 plus 0.7 times v final squared. I subtract 5.39 from both sides of the equation. 19.81 equals 0.7 v final squared. Then we just need to solve for v final. So v final squared equals 19.81 divided by 0.7, that's 28.3. So v final, not v final squared, is the square root of 28.3, which was 5.31 meters per second. Now that we've walked through it, you can kind of picture the thing. The bowling ball comes rolling down the track here at 6 meters per second, and then it goes up a hill. As it goes up a hill, it slows down a little bit. Didn't slow down much, but it slowed down to 5.31 meters per second before it got to the end here. I know the math looks crazy, but if you follow it stepwise, it's not that bad. And if you get lost at all while you're doing it on the real exam, show me your work and I can kind of see how far you got before you got a little bit lost and can give you partial credit. So this problem is probably easier. The number 13, Ultimately, we can figure out the velocity of each of these things as they roll down the ramp, and then use that information to figure out, which one has a greater rotational kinetic energy. But what we do is gravitational potential energy at the top of the ramp, mgh, no v squareds, no nothing else. It's just that straightforward. mgh equals 1/2 mv squared. So that'd be the same for both things. There's no difference in the solid or hollow for mv squared. But where the difference comes in is when we're doing the 1/2 I omega squared. 1/2 I omega squared, I, moment of inertia, is different for the solid cylinder or the hollow cylinder. The solid cylinder, 1/2 mr squared. The hollow cylinder is just mr squared. What the moment of inertia means, it's how the mass is distributed around the axis of rotation. The hollow cylinder, all of the mass is as far from the axis of rotation as it can be, and that value is mr squared. For the solid cylinder, assuming that it has uniform density throughout the solid cylinder, it's essentially the average mass is somewhere between the middle and the edge because it's evenly distributed throughout. So that one works out to be 1/2 mr squared. When we do that, we can figure out the velocity of each of these rolling things, cylinders, I guess. Each of these cylinders when it reaches the bottom of the incline. And if we know their velocities, we can figure out what the greatest rotational kinetic energy is between the two. Okay, 7, 9, 10, 7, 9, 10, 14, and 13. So 14 is another question I have. So what is going on here is a net torque question. Torque, we will all remember, is force times lever arm. Now, it depends where the force is being applied, how much torque will be involved. So there is, around this elbow joint, some downward torque. That downward torque is counterclockwise. Counterclockwise, we will call negative. No, sorry. I will always struggle with this with all my life, and I don't know why. As any of you who might be able to look at a clock will tell me, this rotation is clockwise. This clockwise is negative. Counterclockwise, which you might otherwise think would be, against normal, so maybe you'd call that negative. Counterclockwise is positive torque, clockwise is negative torque. Just by convention, somebody decided it would be so, and that's what we do. So, if we are looking at what we're going to call downward torque, the clockwise torque, part of that torque is a force due to the weight of this baseball. The weight of the baseball, they told us explicitly, was 0.750 newtons. Where that baseball is located relative to the axis of rotation, the elbow joint, is 0.22 plus 0.22, 0.44 meters away. And so we have a contribution of downward torque from the weight of the baseball. There's another concept that we're going to hit right here. That one we went through pretty quickly, but it was called center of mass. I don't know how much every bone and muscle and blood vessel and everything in this arm weighs, but if we assume that it has uniform mass throughout, uniform rod with a mass of 1.5 kilograms, then we can pretend that all of the 1.5 kilograms is located at the center of mass. So the weight of the arm is going to be the 1.5 kilograms times 9.8 meters per second squared. They gave us just mass here. They gave us an actual force for the ball. Kind of tricky. So we have mass times acceleration due to gravity, and we're going to pretend all of the mass of the arm is located at the center of mass, 0.22 meters from the axis of rotation. So for the arm and the ball acting together, we get a certain amount of torque, 3.56 Newton meters. That's what we use to describe torque, Newton meters, that is going to give the arm clockwise rotation, unless this biceps muscle is strong enough to overcome the weight of a baseball and the arm itself. So there we need to figure out how much upward torque there is. This one's easier because we've been told that the biceps muscle will exert a force of 12.6 newtons, and it is attached 2.75 centimeters. So 2.75 times 10 to the negative second meters away from the axis of rotation. And that one will give us an upward torque of 3.47 Newton meters. Well, in that case, this thing's going to rotate down. The net torque is torque up minus torque down. The upward torque is 0.347 minus the downward torque, 3.56, is negative 3.22 Newton meters, meaning that a negative torque is a clockwise torque, and this thing will rotate down. This person just is not exerting enough upward muscle force to hold the ball, and so it flops down. That's number 14. Okay. Clear all drawings, close the drawing tool. So rotation and torque, that's stuff that came up, recently. Hopefully you're feeling okay with conservation of momentum. It's a fairly simple concept that the initial momentum of the system equals the final momentum of the system. So the football player who is running has both mass and velocity. Momentum is the product of mass times velocity. The football player who is standing still, jumped up in the air, not moving, that person has no initial momentum, but after they collide and stick together, the initial momentum is now distributed over the mass of both participants. And so we will be able to either figure out a final velocity, or in the way this question was phrased, we're able to figure out a mass for the receiver. We knew the mass of the tackler and the velocity of the tackler. And so we had a question, now that we know their final velocity, how much mass does that receiver have? And if you're looking for reasonable numbers all the time, sometimes I pick bad values for velocities, and we would have a tiny person as our receiver. It just happened. And this conservation of momentum is in both axes. So one car carried x-axis momentum into the collision. The other car carried y-axis momentum into the collision. When they collided and stuck together, total momentum is conserved. So because we have an x value and a y value, we can do our vector addition from way back when in the course, a squared plus b squared equals c squared. And we can figure out that the final momentum of the system is 48,000 kilograms times meters per second. And the angle is inverse tangent of opposite over adjacent. So opposite is the y-axis, adjacent is the x-axis. 30,000 divided by 37.5, inverse tangent. Get 39 degrees north of east as the direction. And we could figure out the final velocity based on the final momentum and the combined mass of each of the cars. The exam on Friday will be of the sort that is a little annoying in that you will see a space for showing your work after each question. Some people choose to do it that way, and that's fine. They just type in the box, oh, I did this, and they're happy with that. I'm happy with that. It's fine. If you just upload an image and you upload it to the exam itself, all you have to do is tell me at the beginning, hey, I'm going to upload an image at the end of the exam, and then do it, and I'll know it. Otherwise, just let me know, hey, I'm going to email you an image, and I'll make sure I look for that before I try to evaluate partial credit on your exam. And any of those things are fine. Okay. That is all the questions I see in chat. If you have other questions, I am delighted to spend some time trying to make sure that things make sense for you. If you don't have questions and you just want to get on with your day, I'm fine with that too. So, so I'm seeing other questions come in. If you have to go, you can go, and I won't feel bad about it. But if you have questions that are popping into your head now, I'm getting a question on number 15. So I'm going to spend a little time going over that process. And then, you know, if anything else pops into your head, go ahead and ask. And yes, you can upload your images for your work on the exam, and that is perfectly fine. So we have a 100 kilogram sled that is sliding along a horizontal surface. There is friction. Coefficient of kinetic friction is 0.15 for this situation. Sled has a velocity of 18 meters per second when it starts, and then later on it slows down to 3 meters per second. And so we have some questions to answer about this thing. What is the frictional force acting on the sled? We even remember friction? Well, it's got weight equals mg. So it's 100 kilograms. So 100 kilograms times 9.8 meters per second squared. 100 times 9.8. I could have done it in my head. 980. Weight is 980 newtons, which means on a horizontal surface, the normal force is 980 newtons. And so the force of kinetic friction is the coefficient of kinetic friction times the normal force, which would be 0.15 times 980 newtons times 0.15, 147 newtons of frictional force. Friction is negative because it opposes motion. So if we're taking, this direction to be the positive x-axis, then friction is directed in the negative x-axis, negative 147 newtons. Okay, here's another question. What is the change in momentum of the sled? It's just a different question. Change in momentum equals final momentum minus initial momentum. Change in momentum equals mass times final velocity minus mass times initial velocity. 100 times 3 meters per second minus 100 times 18 meters per second. Come up with a big negative number, negative 1,500 kilograms times meters per second. Then finally, I guess this is the punchline, the real reason that we were, doing this question on this exam. Impulse momentum theorem is F delta T equals change in momentum. We have a force, that's the kinetic frictional force. We have a change in momentum. We want to know how much time it took. Delta T equals change in momentum divided by force. The change in momentum was negative 1,500 kilograms times meters per second. The force, we said, was negative 147 newtons. And so all of that cancels out, but to leave us with seconds of 10.2 seconds for that to happen. Kind of a long multi-part question, but a question that kind of assessed a few different concepts in one question-ish. I guess 3 subparts, so not really one question. All right. That takes me to the end of all questions that have been asked so far. Happy to go over anything else that people are wondering about. Happy to let people go about their day if they want to do that instead. Any other questions?
I think I just missed it when you explained it the first time, but in 14, why is the length of the arm 0.22 meters instead of the total 0.44?
So for the baseball is located at the very edge, so that's the 0.44. For the weight of the arm itself, we're doing center of mass, and the center of mass is located at the center, so that would be the 0.22, halfway between the elbow joint and the fingertips.
Okay, thank you.
Sure. All right, I will post this recording. I will check email if you come up with a question and you want to shoot me an email. You have all the resources. There's a video walkthrough of the practice exam key. So any other questions you have, hopefully get a chance to get those answered before the exam on Friday. So good luck, study well. I hope these days aren't too stressful, and I will see you on Friday. Have a good day, all.
Professor,
Yeah.
how long do we get to take the exam?